So let me point out, for future reference, I marked which were the most important projects in each section to guide people. The command injection, that one has various ones where you get used to how to do normal high-level command injection. 202 is where you learn the simple, basic buffer overflow. That's the root of all memory corruption vulnerabilities. And this is the most important one here, 308. These first two are just getting a Windows server of some sort running. You can put it on the Google Cloud or you can put it locally in a virtual machine. Either way works. So I've got mine in a virtual machine because the Google Cloud one stopped being free, and that annoyed me. So I made a local installation. So here's a local copy of Windows Server 2016. It's a trial edition, so it will expire after a while, although you can extend that pretty far, but not forever. And so I've got a local IP address of 172.16.123.248, and I turned off the firewall. And I'm running this thing called Vuln Server, which is fantastic. This is on GitHub. It's an open source project. You can modify it and compile it yourself. And it's very nice to do so. Let's see if my webcam is on. Good. Anyway, so all you do is double click Vuln Server and it will run right here. It's listening. And see, I tested it a couple times with client connections. This thing is just intended to look kind of like an email server. It's just a server with various functions, and it has all sorts of interesting vulnerabilities. And what we're going to do here is exploit the simplest one, just a simple buffer overflow on Windows. But this is where you really get to the heart of understanding how Windows exploits work. So you need we'll need some tools on our Windows machine, and we will need to attack it from some other machine. If you're using the Google Cloud for your Windows machine, you can use the Google Linux machine. Other than that, you'll need some other machine to send the attack in. It doesn't really need to have much on it other than Python. So I'm just going to do it directly from my Mac host, which has the ability to run Python just right here. I don't need a second virtual machine. I can use a real Mac as this. You could use a Kali virtual machine or anything, as long as it has some way to reach your Windows machine over the network. So you have to turn off the firewall, make your server discoverable and all that jazz. And then you should be able to connect with Netcat. So my address on my Windows machine is 172.16.123.248. So first let's start by pinging it. Almost all my students have trouble with networking problems, so this is always the first step. First, turn off all firewalls, then make sure you can ping. And if you can ping, then you try to connect to that server, and it runs on port 9999. Okay, and you've made it. It says, welcome to vulnerable server. If you say help, it has a variety of commands. These are commands that take an argument, and it has a whole series of vulnerabilities. And the one we're going to use today is trun, which has a simple basic buffer overflow, which is good enough for what we're doing today. So I'm going to exit. All right, and so we just repeat everything we've done on Linux in a Windows environment, which, as you will see, is very much the same, but it is rather prettier. In Windows, of course, everything has graphics. And although Linux does have GUIs, we haven't been using them. So we start with a fuzzer. So let's take a look at the fuzzer. VSFU is what I called it. All right, so here's my fuzzer. It's a Python script. I import the socket library, so I have raw network sockets, so I can do a netcat. I specify the server IP address and the server port. Now I get the length from the user, and now I open a socket, connect, send capital A times the length, and the format for this is trun space period, and then the attack. That's just the format it takes for this server. So it will send the A's, and then if anything comes back, it will print it and close. This is a very simple fuzzer. So if I run that, let me run it here, and what I'm going to do is move the instructions off the visible screen so you can see my target here. So here's my Windows machine, and here's my attacker. So if I send 10 characters, it works, and it does not crash. It says run complete and goodbye. That's what happens when it didn't crash. So if I send 100, it also works. If I send 1,000, it also works. But if I send 10,000, it crashes. And you can see here when it had an unhandled exception, the Windows operating system detected that the program stopped, and I can close the program. So somewhere between 1,000 and 10,000, there is some kind of bug. And this is how you do fuzzing. You send junk to the server, random packets, until you make it crash. Then you analyze the crash to see if it is so-called exploitable. Exploitable means you can turn it into something more powerful, like the thing you would most like is a remote code execution exploit. So I'm going to run vuln server again. And let's try some other lengths here, like 2,000. 2,000 crashes it. Okay. And 10,000 crashes it, and probably anything between 2,000 and 10,000 will crash it. So we've now found a crash that we can analyze. All right. So to find out what happened, we use immunity. Immunity is the equivalent of GDB for Windows. And so you start immunity here. Here's the immunity debugger. It's just a free download. And this does the same thing GDB does, but it has nice graphics. So now you can open that file here. I can open vuln server, and it will load it in memory and then pause. So now I see the beginning of the program. These are the addresses. Notice how it jumps up by 4, 48D0, because it's just showing the size of the instructions. By the way, it's not always 4 here. So this is the raw bytes for the assembly language command. This is the command. Move this, jump to ntdil, some part of Windows, load this address, move something, do a sysenter. This is the assembly language instructions. Down here, you've got a pane where you can just dump any region of memory, and you'll just see the hex and the ASCII in it. So anything of interest you can examine there. This is the stack. That's why it jumps up by 4. This is a 32-bit program, so I'm seeing 32-bit code here. And so I just have a series of addresses on the stack. Notice this one pointing to the entry point. All code sections all think they are in 400,000 on Windows. That's the default. They load into a virtual address of 400,000 and change. So your executable code you'll find with addresses like that. This should look rather familiar. These are the registers, EAX, BC and D. Here's the stack pointer and the base pointer, and here's the EIP. So right now it is stopped at ntdil because remember what I said before. Whenever you're doing reverse engineering, the tools show you too much information, and the easy to read stuff is always on the right and at the bottom. This is the most important information. Paused. The program is not running. When you open a program in the debugger, it loads it and stops so you can examine it. It doesn't run it until you run it. And if you're running a 32-bit program on a 64-bit OS, you have to run it twice. So here's the run button. I run it, and now it pauses again because what it's done is load the Windows on Windows 32-bit virtual environment to run 32-bit code on 64-bit 64-bit OS. And now I have to run it again, and now it's actually running. And since it's running, it's actually opened the window over here that it runs. So it's running and showing the data in that window, and now we can send it an attack. So let's send it 2,000, and it crashes. So notice what happens here. It's paused again, and at the bottom it tells me what happened. Access violation when writing to 41414141. So I just sent 2,000 capital A's, which is all 41s. So somewhere in that 2,000 A's is an address, and it tried to write to that address, and that address is not a valid address for this program. Programs can only use certain addresses, and let's take a look at that. If you go to Window, maybe it's View. Where's View? Well, there, View, Memory. You can see the memory map of your system. And this thing is called vuln server. And you can see the sections here. There's the text data, R data, stack segment, and another data section. And you can see where they are. They're all pretty much starting with 400,000. So 41 is a gap here. There is an address starting with 41 is not legal, although I guess I should go down here. It would be 41, 41, 41, 41. It would be in this gap. That memory, even if there is some actual RAM at that memory, which there probably isn't, I'm not allowed to use it. It has not been reserved for the use of this program. So it's going to give me an error when I try to write to it. However, this is not the easiest kind of attack to exploit. I've now got control of a write operation. Now, we talked about this before with format strings and heap overflows. You can take over the machine with a write operation, but it's not the easiest thing. So I'm going to get started again. Now, I can't send another attack until I restart the software. So I have to hit debug, restart, and say yes to kill the old one. And now it's loaded again, but it's not running again. It's paused. I have to do run and then run a second time. Now it's actually listening. Now I can send another attack. So let's send 3,000. When I send 3,000, it crashes, but now it's access violation when executing 41, 41, 41, 41. And this is why I said earlier, once you find an exploit, never change the length of your attack, because a different length might cause a different crash. So I have found that by sending 3,000 characters, I gain direct control of the instruction pointer. Some of the A's I put in ended up in the instruction pointer controlling the next address. So this is the simplest thing the simplest form of exploit to develop when you have direct control of the instruction pointer. So that's what we're going to do. We'll work on this one to get started. That is the simplest buffer overflow, and you get there by sending in 3,000 characters. So we talked about all this. We observed the crash, sent 3,000. Okay, so now we just need to find out which of the A's, which of those 4,000 A's got in there. There are various tools to create non-repeating patterns of characters. I just wrote my own because it's pretty easy. So if you do VS, this is EIP0. Okay, so all this does is it counts from a 0, the numeral 0 to the numeral 5, and then 0 to 9, and 0 to 9 again. So this is 500 times it makes 4 characters, which is 3 numerals and then a capital A. So if I run that, okay. All right, let's do it with Python. That'll be all right. All right, that's all it does. This is 3,000 characters. And the only thing special about it is any 4 characters in a row are unique here. I can tell from those 4 characters where I am. So if I use this for my fuzz, instead of just 3,000 times A, I'll be able to tell which characters ended up in there. So I make this one called VSEIP1 because this one just prints it on the screen. The EIP1 makes the network connection. So I'm just copying code from before. I just connect to the right IP address and the right port. And then I sent it 1,000 A's. So I guess that's right. This was only 2,000. This was 500 times 4. This was only 2,000. So I put 1,000 A's at the start. Then I put in 2,000 non-repeating characters. And then I send that to the server. So this should crash. And where it crashes should be more informative. So I restart this guy again. Debug, restart. Yes. Run and run again. So now it's listening. And then I run this one, which is VSEIP1. I don't know if I got to put Python before it. I don't. So now it sent it, and see, it now crashed, but instead of 41, 41, 41, 41, it crashed at 35, 32, 41, 31. Now remember, 31 is the numeral 1, and 41 is a capital A. So that is 1A25, reading from right to left. So 1A is here, and 1A25 would be around 251A, where it's going to be. Anyway, let me check my instructions. It is unique in there, and I found it there. It's, yep, A252 is where that is. A252 is here, so that's 2A51 there. And that should match what I have in immunity. There, I have 52A1. And here I have, oops, it's here. 5.2, no, losing my mind. 5.2, oh, it's backwards. Okay, remember, because of Little Endian, it's backwards. So here I see 5.2A1, and that means reading from the right, 5.2A1, there. Those are the characters that hit the instruction pointer. So I can figure out that it is 250 times 4, that's 1,000, and then 2 more, 1,002 plus the 1,000 before. So anyway, I can figure out where the instruction pointer is. That's the point of this, and that's what I have here. Turns out I need 2006 A's, and the instruction pointer is there. So this is VSEIP2, and I got to get out of this first. There. So now it connects to the right server on the right port, and now it prints 2006 A's, then BCDE, which I'm hoping is the instruction pointer, and then enough F's to make a total of 3,000 bytes. That's what it sends, prefix, EIP, and padding. So this will just check to make sure I'm really hitting the EIP. So I have to restart it again, debug, restart, yes. And I have to run it and run it again. And now I can send that stuff, which is VSEIP2. And now it crashes with BCDE. 41 is A, 42 is B, CDE, and that's what I wanted. So now I control the instruction pointer. Okay, now, all right. Now we can examine the memory at ESP at the crash by following a dump. See, now we control the instruction pointer. Now we can ask, what shall we put in the instruction pointer? So let's take a look at the point of crash here. So notice here, the stack pointer is pointing to FFFF. Now remember our exploit. Our exploit consisted of 2006 A's, then BCDE, then something like 1,000 F's. So at the point of the crash, the stack pointer points to F's, which I injected. So if I could put my shell code here, I could run it. So somewhere in all those F's is what the stack pointer is pointing to. And to find it, you can right click here and follow in dump. And now it'll show you all these F's here. And if you just scroll back, you'll see that in fact, it's pointing to the very first F. So that is really convenient. So I can put any address I want here, and then the stack pointer points right here. Now this is important because I have address space layout randomization turned on, and I can't easily turn it off. So I'm not going to be able to inject a literal address of this code because the address keeps randomizing. What I'm going to do is trampoline. I'm going to find a jump ESP that doesn't move, and I'm going to put that address in. And it will go there, execute a jump ESP, and then it will run code right here where the stack pointer was. So I can find my way back to here even without knowing the absolute location of that code in memory. That's return-oriented programming. So again, you got bad characters, and it turns out these are the bad characters. And you can do the same thing. You can run an attack that sends a whole range of characters here and see if they get there. I'm not going to go through it all, but you can do that to find your bad characters. And then when you're done, you now know how to generate exploit code using Metasploit that dodges the bad characters. So now we need to find code to use. We need to find something the developer put there that doesn't move. If everything was randomized, it would make buffer overflow exploits almost impossible. But it turns out not everything is randomized. There's a plugin for immunity called Mona, which is awesome. Mona is a framework like Metasploit and Wireshark. You can add more code to it, and the open source community has. So Mona is designed to help developers find exploits. So all you do, it's a Python script. All you do is download it and put it in the right folder, and the immunity debugger will find it. And then you can look at the module. So I've already got it here. So I'm going to run Mona, bang Mona, modules. That's how you run it, although you do have to spell modules correctly. All right. And so it runs, and it prints out what it finds. And so it finds all the modules that are running. And let me make this as big as I can. Okay, so here's various things running, and I I can probably make my window a little bigger. There we are. So here's something in the kernel. Here's something called bcrypt, some kind of cryptography. Here's Vuln server itself. And here is a DIL used by Vuln server, ESS func. So notice it tells you which defenses are turned on. This is where they're loaded in memory. And here's defenses. Now rebasing is for libraries, and it tells you whether libraries have to always be located in the same place or whether they can move if there's a collision. So false is better, but true is not fatal. However, here's the thing that we really don't want, ASLR. These modules with ASLR equal true are going to randomly relocate every time we restart. So we can't really use any of these addresses. So there are only 2 modules that don't use ASLR. And by the way, this is because Vuln server was compiled without ASLR, without position independent executable. So if you run old software on a new version of Windows, it can't always save you. That's the fundamental problem. Anyway, so Vuln server itself never moves in memory. So we could try finding code in here. The problem is this code loads where the main executable code always goes in Windows, which is at 400,000 in hexadecimal. And that means all the addresses of this code start with null bytes. So I can't jump to any of this code without injecting null bytes. And when I'm using strings, I can't really do that. I see a question, how does immunity compare to x32 debug and x64 debug? They both do essentially the same thing. And a lot of people like x32 and x64. Immunity is older. I mean, even older than that is Ollie. They all do about the same thing. I never got used to x32 debug and x64 debug, but they're good products. And I know a lot of people like them. One of these days I might upgrade to them. Anyway, so here's the module ESSfunc.dil. This one also doesn't move, and it starts at page 62. So these addresses, many of them don't have null bytes in them. So this is my target, ESSfunc.dil. So now all I need is to find a jump ESP in ESSfunc.dil. And that is such a common thing that Mona has it all ready to go. So there is, in fact, another shortcut you can use in Mona. But when I did this, I was using an older tutorial where you had to specify the code you're looking for. So I actually used Kali. Kali has an assembler called NASM that we use in some of the other projects. So if you compile jump ESP, you'll find that it's FFE4. So if I can find FFE4 anywhere that doesn't move, I can load that address in, and that will come back and go to code under my control. So you find it with this command, Mona find the sequence FFE4 in the module ESSfunc.dil, which is the module here that doesn't move. So I should be able to put that in. That's the command. And there it goes. Mona found 9 of them. There are 9 occurrences in that module of these bytes. So I could jump to any of these. They'd all be fine. The only thing that could still go wrong is they might contain forbidden characters. It doesn't look like any of these do contain tabs or anything. So 6250 11AF is the first one, and that would be good enough. Any of them would be good enough. So I just take the first one. So now I want to test code execution. These are exactly the same steps we did with Linux. So if I cat vseip3, oh, well, looks like I didn't have this one from before somehow. I'll put it in now. I'm going to copy vseip2 to vseip3 because there's an IP address problem. So I want to keep this part the same and this part the same. The guts, the only part that changes is in here. This is what specifies the server's address in here. Mona also contains functions for finding any kind of, oh yes, yes, it totally does. Caitlin is correct. Anyway, I say if you look for, there are other tutorials, there are some more advanced functions in Mona that make it even easier. I wrote this using a tutorial, I think Mona was in a more primitive state. Anyway, so that's vseip3, and the point of this one is it will now have a 16-byte NOP sled. It'll feed in this address, 6250 11AF. Let me make that bigger. There. And then it will feed in 16 NOPs and a break. So I'm just making a little 17-bit shellcode to see if it will run. All right, so that's what happens with VSEIP3. So let me go back to my instructions, see if I want to put breakpoints in yet. Okay, nope, I want to just run it. So let's go here. View CPU is the default view, and then debug restart. Yes. And run again. So it shows running. And now I send my attack, which is here, VSEIP. And so it sends the attack, and here it hits an int3 command. This is what I wanted. Here's where it stopped. And if I scroll up here, you'll see I was able to execute this code, nop, 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 and then int3. So I didn't do anything yet, but I proved that I can execute code. So all I have to do is put a better code to run, and I can take over the box. And by the way, this is the address I injected, 6250.11af, being interpreted as commands by Immunity, but it isn't. It's really an address I injected. And up here is the A's. This is what I put in instead of B, C, D, E, and this is where I put in my shellcode. So I'm now able to reach code despite address layout randomization by trampolining back to the stack pointer, and I'm able to execute code on the stack. So I seem to have everything I need to complete my exploit. And so that means all you need is to generate exploits here. So you use MSF Venom again now to make Windows malware. You can use Windows Interpreter, and it'll give you the Python to make the code, and then you're ready to go. So you can run the exploit and get a shell. Now here, I don't know if I have Metasploit on my Mac. I think I'm going to have to run Metasploit on my cloud server. So let's do this. It looks like maybe I do. Let's see. I have sudo msf console. All right, I do, perhaps. I do. Okay, good. So I'm going to stop that. So I think I'm all right, but I wonder if I've got the right IP address. So I'm just going to try it and see, because I demonstrated this in one of my classes recently. I think I've got good enough versions here. VS shell, I think is my exploit. Yep. So let's take a look at cat VS shell. All right, so here's my exploit. I connect to the right socket. I inject the trampoline address that will come back to jump ESP. I put in 16 bytes of NOP sled. By the way, I should mention I had to learn this the hard way. Metasploit code that avoids certain characters has to start with a decoder. And some of the Metasploit unpackers actually use bytes outside. If you don't have at least 16 bytes of NOP sled, when using Metasploit payloads, they tend to overwrite themselves and destroy themselves. This made me crazy for several days to figure this out. So I learned as a habit, always have some NOP sled before a Metasploit payload or you will suffer. Anyway, so I have some NOP sled, then I have my exploit code, then I have enough padding afterwards to do it and send it. Now this Metasploit code was generated with my command and control center's IP address in it. This is using a reverse shell. This is the right kind of attack in the real world. You specify the IP address of the host here, and I'm hoping I made it right. 443, I may have to regenerate it, but I'm going to just see if my demo will work the way it is, because I think it did before. So I'm going to run that, which is VS shell. I'm going to have /. Okay, there it is. Now let me restart my debugger. Debug, restart, yes, run and run. Okay, and now if I go here and run this shell, it will inject code and run it here, and then start to try to phone home. Now it's not going to be able to phone home to the command and control server unless it's listening. So before I send the attack, I better start my listener. So I've got to do sudo msf console. Give it a thumbprint. And then I've got some boilerplate commands in Metasploit. This is the stuff that starts listening for a machine that's exploited phoning home. So the multi-exploit handler is listening, exploit, now it's listening, waiting for victims to phone home. So my victim is running, my attacker is ready to go, and my command and control server is listening. So I send the attack, and it worked. That's what I thought. So it ran here, see it's running like crazy doing stuff, and what it's doing is phoning home to my command and control center, and now I have a interpreter shell. So I can do get UID to see who I am, and I'm the administrator, and I can do help to see all sorts of other things I can do. I can turn on the webcam, turn on the microphone, steal password hashes, open a normal command shell, restart the machine. You know, I can do all the goodies that Metasploit can do here, like any remote access Trojan, which is essentially what it is. But I didn't have to trick someone into downloading and running poison. I exploited a process and injected the poison. Although, if they had antivirus running, it would totally have caught me because Metasploit payloads are well known in public, and antivirus will bust you. But, you know, that's the heart of it. And now all future Windows exploits are just adding bells and whistles on this, just like that basic Linux exploit is the heart of it all, and all future exploits are just modifications based on it. By the way, there are some Windows defenses you have to turn off to do this exploit as listed. If you forget to turn them off, it will get stopped. Anyway, so that is the most important Windows project for you to do, 308. And the others are just adding bells and whistles, and I'll talk about them a little later, but that's enough. I'll probably just go over these briefly in about 20 minutes, and that's probably as far as we're going to get. I think this whole workshop ends in less than an hour. So I'm going to stop the recording.